Okay, I'm just going to do a few more examples of limits at infinity. So for the next example, let's look at the limit as x approaches infinity of e to the power 5 minus x. Well, let's see. This is a composition of functions, right? This is an exponential function with 5 minus x, a linear function, plugged inside it. So we can approach this like we did with other compositions, where we start by taking the limit of the inner function. And as you know, I like to approach this with this notion of u substitution. We're going to have u equal 5 minus x. So now what's going on with u? Well, we'll take the limit as x approaches infinity of 5 minus x. So this, if you just think about what's going on here, we're going to have 5 minus large numbers, right? As x approaches infinity, we're getting bigger and bigger numbers, and we're doing 5 minus those numbers. So what's happening here is as we do 5 minus large numbers, we're going to get large negative values. So this will be approaching negative infinity. So that means that we have a situation where as x approaches positive infinity, u is approaching negative infinity. So now we will do a substitution of variables. We are now going to convert this to the limit as u approaches negative infinity, right? The corresponding value that u is approaching of e to the power u. And you may recall e to the power u, if we think of it as this is the u-axis and this is our y-axis, e to the power u is this function, and as x approaches negative infinity over here, we have it approaching 0, right? So this limit equals 0. I cannot stress how important, I can't stress strongly enough how important it is to have this picture in your head, okay? Have this picture in your head and know that, for e to the x or e to the u, on the left side, it approaches 0, right? And if you swap that and make it e to the negative u, then you flip it around, and then it approaches 0 on the right side. Just having that in your head memorized and having a visual image of it is really useful. So there's one example. Let's do another example. Let's do, I think this was one I did on the first video, I drew a picture of it. It was the limit as x approaches infinity of cosine of x divided by x. I drew you an image of that. And I said that this was going to equal 0. But now, let's look at a proof of this fact. Okay? I just drew you a picture and told you the answer. But I didn't really explain why. The proof uses our friend, the Squeeze Theorem. At least one proof does. There's another way to prove this, which we'll learn very soon when we get to L'Hopital's rule. You can apply that here. But you can also prove this with the Squeeze Theorem. So here's how you prove it with the Squeeze Theorem. Well, here's what we know for sure. We know that cosine of x is bounded between -1 and 1, right? That's how you start a Squeeze Theorem. And then what we can do is say, well, x is approaching positive infinity. So, since x is approaching positive infinity, we can assume that x will be a positive number. We only care about very large positive numbers. So in particular, x is positive, which means it's not 0 and it's not negative. So that means I can divide everything by x and get the following inequality. Okay? I divide all 3 parts of this inequality by x, and it produces this inequality because x is a positive number. Okay, so the left and right sides are -1 over x and +1 over x. And the cosine of x divided by x, the function we're interested in finding the limit of, is squeezed in between them. So now I just have to do the limit as x approaches infinity of -1 over x. Well, this is negative limit as x approaches infinity of +1 over x. But +1 over x is approaching 0. So that's 0. And, likewise, the right-hand side is that +1 over x, which I just said is approaching 0. Right? So the left side approaches 0, the right side approaches 0, and so therefore by the Squeeze Theorem, this limit approaches 0 as well. Okay? So, here we go.